Welcome, everybody. My name is Adam Frey, and I'm the Director of Global Campaigns for Software at 3D Systems, and I want to thank you for joining today's webinar on reducing delivery time and increasing mold quality with the right CAD/CAM solution. On today's webinar, we will discuss the following topics. What are the main challenges mold makers are facing today? What are the 5 key elements you should look for in a CAD/CAM solution? How to reduce your mold design and manufacturing time by up to 50% with Cimatron? What mold design best practices are used by the industry leaders? And how innovative mold design and manufacturing capabilities can help you leapfrog the competition. A few housekeeping items before we get started. As you may have noticed, all attendees' lines were muted upon joining the webinar. However, we do encourage you to ask questions during the webinar. Therefore, please use the Q&A button on your screen to submit any questions as we go along, and we will take time at the end of the webinar to address questions that were submitted. If we don't get to your question, we'll be sure to follow up with you after the webinar with an answer to your question. Also, we are recording this webinar and we'll be distributing the recording to all of you after the webinar. So once again, thank you for joining us today. And at this time, I'd like to introduce Dan Branch, the Cimatron Customer Support Manager at 3D Systems, as he will be leading today's presentation. Dan, it's all yours.
Thank you, Adam. Well, the manufacturing world continues to evolve, and the pressure on manufacturers keeps growing. The success of mold makers like you all depends on your ability to deliver high-quality tools at the shortest time and lowest cost possible while being the most productive. Without question, the CAD and CAM software you use plays a critical role in achieving these goals. You need a system that'll help you work faster and easily handle changes, a system that includes the right analysis tools and that works with you to eliminate errors and mistakes. You need a system that will enable you to manufacture molds with superb surface quality, a system that will guide you to be more productive using automation. It's really just absolutely critical. You need to make sure that you're using the right CAD/CAM solution. For this webinar, we went out and asked mold makers and prospects what the main challenges and pain points they face are. The top responses were working with multiple solutions. Multiple systems for CAD and CAM can lead to data transfer errors, working with the wrong data, and not being able to work concurrently, resulting in increased manufacturing time. Lack of mold-specific functionality and automation. General purpose software is common, but the lack of automation is inefficient and it's time-consuming. Working with complex and large molds. Their current software can't handle the heavy data requirements of very large projects. Handling changes. Their current software has no provision for processing engineering change orders, so they may have to even start over when a change arrives. And subpar technical support. The available support staff just can't assist with complex mold-related issues. It isn't local, or it doesn't offer live assistance. It's very likely that many of you can identify with some of these points. There are many CAD and CAM solutions on the market. Some focus on the design CAD side only. Some focus on the manufacturing CAM side. Some are general solutions for manufacturing, and some are dedicated solutions for NC tooling. But if you look at those main pain points in the tool shop, and you also consider the main goals that mold makers would like to achieve, what they reveal are 5 key elements to look for in the right CAD/CAM software. 1, an integrated CAD/CAM solution will deliver molds faster. With a single interface from design to manufacturing, you can maintain data integrity throughout the whole process. Also, eliminate data translation errors, and even save time by ensuring that every department is working on fully up-to-date information. 2, dedicated CAD and CAM functions will boost productivity. Despite the many softwares on the market, it's important to look for a solution with functionality specific to mold design and manufacturing. These features will help you be more efficient and ultimately deliver molds faster. 3 is cutting-edge technology and innovation. Maintain a competitive advantage with new capabilities that help you deliver faster, better-looking, low-cost molds. It's important to pick a software solution that knows the latest mold-making technology and a software vendor that is committed to regular updates with new features that you can integrate into your existing workflow. 4, ease of use. Look for an intuitive user interface with built-in tips and help menus. Look for automation and standardization features, as these will make both design and NC programming easier by reducing button clicks. Ease of use pays off when training the new generation of employees and also with those who are already using the system every day. And then lastly, 5, a quick return on investment simply means that you want to see the results fast. Your investment in a CAD/CAM system should immediately start to pay for itself and do so every year. We know from experience that mold shops that have switched to an integrated CAD/CAM solution that's dedicated for tooling have reported shorter delivery times of up to 50%. So if you have any doubt that such a solution exists in the market, the answer is yes. And that's why we're here today to present Cimatron. Cimatron is an integrated and dedicated CAD/CAM solution for the design and manufacture of molds, dies, and tools, designed to meet the unique challenges faced by mold makers today. It enables you to deliver high-quality tools of any size and complexity in record time. With its wide range of applicative functions, as well as a full range of CNC technologies, from simple 2.5-axis milling and drilling to complex 5-axis machining, Cimatron users can dramatically increase their productivity, competitiveness, and profitability. As Cimatron is a comprehensive solution, I really can't show you all of the capabilities it has in a short time, but I can focus on some of the unique tools and approaches that we can help you with and achieve your goals and overcome the challenges that we've just laid out. The Cimatron design environment was built with mold makers in mind. It includes analysis tailored for plastic parts and applicative functions that automate because they understand the way a mold works and know what you need to do. It's also there to help for the common frustration points in the design process. For example, the changes to the part that arrive while design and manufacturing are well underway. Drafting, part ordering, motion simulation, everything you need for a complete and error-free design is here. The highlights continue with NC programming capabilities that were, again, made to answer the specific needs of mold makers. You can always program any part before the design is finalized, because as the data changes, the cutter paths update to it. As we've said, the system includes powerful 2.5-axis through 5-axis milling and drilling capabilities, and the roughing and finishing routines that contain all of the options you need for precise control. It has automation for fast programming, simulation tools to catch potential errors before they reach the machine, and a powerful electrode design and manufacturing application. So now, let's see some examples of how Cimatron really works. Software for mold design isn't just a slogan. It means knowing how a mold designer looks at a part to be molded and developing useful tools for every step of the process. The QuickSplit function is a good example of this. So while quickly sorting the part faces based on the various directions of draw they need, the designer can immediately begin to visualize the steel components that will make up the mold. At the same time, it's using yellow to highlight areas that should pull, but are blocked by overhanging features. Such an area may need a side action to release, or perhaps start a discussion on a part modification to facilitate molding. At any time, the sorted part can be put into motion or viewed as individual pieces, which reinforces that transition of the geometry on screen from a part to a collection of mold inserts. Developing the shutoff faces from the part outwards also follows the natural thought process of a mold designer, but it requires a full suite of powerful surfacing tools. On complex parts especially, parting design can be one of the most challenging tasks of all, requiring rounds and offsets and intricate blends with tangency control. Cimatron surfacing functions are unmatched in the industry, and not only in their scope and ease of use, but in their automation for mold design. In Cimatron, useful automation can be found in even the most basic of tools. For example, adding cap screws to hold down some slide components can be done through an applicative menu that understands what the catalog part is designed to do and includes some rules to guide the size and location. Popular options while adding parts to a mold are the use of 2 or 4 quadrant symmetry, as well as a snap grid to ensure nominal position values and relieve the effort of adding dimensions. For easy visualization, the size of round parts, like screws, can be set by a circle that best fits the area. And likewise, the length of a screw can be set by a rule, because the correct thread engagement past the target surface is stored knowledge for you to access. Adding parts to an assembly also means that adding a myriad of holes for fit, clearance, threads, and more. These all come free of charge in Cimatron. Each new part knows the components around it and what sort of a hole or pocket belongs in each, even when adding assemblies like lifters and slides. This unique approach to design for tooling continues into the more specific functions built just for molds. Mold inserts are a common need, so whether the situation calls for a simple core pin or a custom shape, an insert design tool is available to help. Inside these tools are options for clearances, tapers, or wedge shapes to anchor the insert in place. After cutting its own pocket, the finished insert remains fully associative to the original plastic part. A mold design is in a constant state of change, so it's vitally important to be working with a CAD system based around intelligent and editable features. For jobs that require a cold runner system, the software lends a hand by storing all of the common runner shapes so that you only need to select a size and the path to take. Options here include cold slug wells and different sizes for branched runners. Gates are also automated, again with every common style available and the necessary shape controls to correctly reach the part. As you modify the gate and consider the preview on screen, feedback about the area of melt entry to the part is provided. The design assembly understands the general structure of a mold, but none of these steps have to be done in any certain order. This allows for a very open flow of design, where known information can be added now, but unknowns can be added later. During mold design, a special data management tool called concurrent engineering can be used to illuminate in the tree the parts and assemblies that other members of the team are working on. This allows each designer to stay up to date as the details are progressing. Vital mold systems like ejection and cooling deserve a dedicated set of special functions. In cooling design, for example, options exist that can cut in an entire circuit at once, or mix that idea with cooling lines based on the requirements of the various standard water fittings being placed. In the case of baffles, the purchase length will be trimmed to fit the contours of the molded part. Rather than estimate this length, your preferred safety distance can be plugged into the system to optimize every baffle for maximum effectiveness while still guarding against unforeseen collisions or breakthroughs. Similar automation exists for ejection design. Because the system is built to understand the function of a mold, telling the pins to locate in the ejector plate is not required. It is assumed, and so saves redundant effort. The length of each pin does not come from user input. Instead, the system calculates the closest standard pin length for any position on the part. Even pin diameters are completely variable during ejector placement so that you can decide on the best size for an area without referring back to the catalog again and again. Ejector pins can be trimmed flat or to the shape of the part and even have additional positive or negative offset. None of this is extra effort because the dedicated function for trimming ejector devices knows what to do. The special conditions of the ejector pin holes are handled in a similar fashion. Clearance lengths are calculated from the part surface down so that the correct hole diameter and purpose is placed in every plate in the tool. Even labeling for the ejector pins and holes has been considered to make sure assembly in the shop is easy and trouble-free. This is also the place where you can ask for an Excel table with every ejector device length and ID on it. And that same type of table can also be made for the baffles we placed earlier. Despite the best efforts of software automation, some checks for design errors are always worth the time to run. To help analyze all of the holes that a mold design sees, we've created a tool to check the various safe distances that you deem acceptable. In analysis, 5 different checks are made between cooling channels, part faces, and drilled holes of other types. Every instance that falls under the safe distance is reported and illustrated on screen so that corrections can be made as needed. Electrical discharge machining is an important facet of making molds. So no software solution for tooling is complete without a full suite of functions for the design, manufacture, and burning of electrodes. In Cimatron, areas that need to be burned are first extracted to a new electrode part. From there, a number of electrode-specific functions come into play. The designer can add step blanks and holders, then remove or extend different geometry depending on the shape and complexity of the area being burned until he's come up with a finished electrode shape. Because multiple locations and mirrored electrodes are extremely common, these are also handled with special functions made exclusively for electrodes. You want to be able to quickly place the correct geometry into new locations in order to reuse electrodes, yes, but also to leverage the design work you already have on hand. That reuse of knowledge actually extends to the electrode designs themselves. Whenever possible, apply a template of your favorite electrode construction techniques and allow them to automatically generate over new areas. As electrode design progresses, you want to get that information out to the shop floor. For some, that means creating electrode inspection and location drawings. This too is an automated process, using a set of options that understand electrode shape and a drawing template that you can easily modify for your needs. Other tool shops are now posting electrode data directly to the EDM machine. The options in the post interface will vary depending on the machine manufacturer, but usually include the type of orbit, size of overburn, and number of tools. Posting directly to the EDM machine assures an error-free transfer of the burn location dimensions and trajectories. The electrodes themselves must, of course, be machined, which means opening the Cimatron NC menus and choosing a strategy. Electrodes are especially well suited for NC automation. They're often roughed and finished in much the same way with the same set of tools. So it only makes sense to apply NC templates for electrode machining. The electrode design carries with it all of the attributes it has to the NC environment too. Information like which surfaces are for burn and which are for clearance, as well as the undersize value to machine. All of this shared information allows for a fast and efficient toolpath with a minimum of user interaction. In the mold making business, being prepared for engineering changes is a must. Because the Cimatron solution follows a top-down approach from the part to design to NC and documentation, there's a fully associative pathway for the new revision to follow, and it provides the ability to update all areas of the process on the fly. The first step, of course, is to simply find and verify the changes in the new revision, and this is done via a real mathematical comparison of the new data to the old. The results of that analysis are grouped and color-coded on the screen. An extra bonus at this step is the ability to add a third part to the comparison, the one you added any draft or molding features to. This filters the comparison result even further, keeping your part preparation work safe from replacement. Once identified, the part changes need to be applied. An update passes them into the splitting model, where the system actually reapplies all of the parting and shutoff work you originally did on top of the new geometry. This amazing recalculation of existing design work might only leave a few areas for the user to sort and check, and reduces the time spent on ECOs to an absolute minimum. The cavities, cores, and other inserts in the mold then fall in line for updating. The parametric and associative nature of Cimatron features means that even if the change has created a conflict in a mold component, the user can pause the action and adjust the design as needed. Real changes require real decisions and often new components, but Cimatron eases the burden by sorting and passing the new data to exactly the places you need it to make those decisions. NC and drafting are just down-level continuations of the ECO process. Whether just started or completely done, they link back to the design, and so also receive updates in turn. A flag notifies the programmer that an update is needed, and the new geometry flows into the stock and procedures of the job. Recalculating the tool paths to recognize the new geometry completes the process and updates the work on the shop floor. Cimatron is well known in the NC world for having rich toolpath strategies that can cut the most complex of parts. But when it comes to pocketing and drilling, automation is the name of the game. For example, automated drill is a highly intelligent function to recognize holes in a part, assign them to groups according to similar geometric features, and then create the toolpath to manufacture them by a known sequence of tools. Auto drill can be defined for any type of hole and be used in 5-axis. The different hole groups are color-coded so that you can easily examine them. The saved drill sequences that are applied to these groups include the order of tools that are needed and the type of drill commands that each one uses. And the whole geometry itself provides the drilling start points, end points, and even gun drilling and breach techniques. The resulting toolpath will be optimized to minimize tool changes, yet keep the drilling logic of each hole as required. The toolpath considers the stock, it prevents shank and holder collision, and it even suggests the minimal clear length to the drilling tools. Automated pocketing works in a very similar fashion. Pockets of different shapes and depths are all grouped into a manager dialog, and then the system applies the best cutter and strategy to rough and finish them with a minimum of user interaction. We're back to a slide here, because one way to examine the Cimatron NC further would be to take a look at some real parts and compare how the surface finish quality stacks up to the competition. Each of the 4 blocks shown here was done on the same CNC machine in an independent benchmark. By using a specially designed algorithm, Cimatron is able to keep sharp edges as well as increase surface finish, all with the same tolerance, same step over, same cutting conditions. The extra attention paid to finish quality and the resulting time savings in polishing is just one example of how the entire Cimatron NC environment caters to the things that mold makers care about the most. So the benefits to machining in 5 axes are very well known. Besides eliminating multiple setups, using any of the many Cimatron 5X procedures allows for the use of shorter tools, which are more stable, resulting in faster machining with less vibration and better surface quality. Automation can even be applied to 5-axis machining. For example, cleanup or finishing routines that were programmed in a regular 3-axis way can be simply switched over to 5-axis with automatic tilting. And if more control is desired, a host of other options can be brought into play to minimize rotational movement or just provide a more stable tool path with the user-preferred motions. One of the key elements that we identified earlier as critical in CAD/CAM for molds was the need to embrace and apply the latest technologies. Now we want to look at 2 instances of that: conformal cooling design and special cutter support. Traditional cooling circuits are often less than optimal for some areas of a mold. Poorly cooled areas in the tool are not good at all. They dictate longer cycle times and cause part warpage and other imperfections. In these cases, it might make sense to use a new idea like conformal cooling and 3D printed metal insert that can include water channels that are able to reach problem areas and remove heat easily and quickly. Cimatron is a part of 3D Systems, the originators of 3D printing. So we're really quick to recognize and support amazing opportunities for mold making that involve 3D printing in plastic or metal. A function to help design conformal cooling circuits is a perfect example. To begin, you select a print-friendly cross-section and then adjust the shape as needed. The basic principle behind conformal cooling is to keep the cooling channels near the surface of the part where they can do the most good. Because this insert will be metal printed, it's totally free from the constraints of drilled round holes. You can prepare open areas in the part or helical paths to drive the channel along. And options within this function allow for a continuous twist or tilt of the section, but the teardrop shape is well suited for printing without any added rotation. At any junction point along the curves, the shape can be changed to another so that perhaps the ins and outs can still be round for standard components or for mating up to other water lines. And another built-in feature of conformal cooling is collision checking. With or without an added safety offset, the new cooling channel can check for contact with existing features like pockets or ejector pin holes. Numerous studies exist that prove the worth of conformal cooling. The more even and efficient removal of heat from the tool pays off tremendously in improved part quality and shorter cycle times. Because not every insert is round, the automation in the conformal cooling function extends well past the ability to build a channel along a spline. Conformal cooling channels can be designed to offset mesh of the part. By stringing the cooling channels around on the offset, you're assured that the cooling circuit is always at the same approximate distance from the surface of the plastic part, which is ideal. The shape of the section and any rotation you add to it contribute to the turbulent water flow and promote maximum heat removal from the nearby plastic. So there's almost no limit to design possibilities when you use this dynamic creation style for conformal cooling channels. The effects of designing conformal cooling circuits are very real and measurable. So we did bring one case study here. This printed metal core insert for a headlight reflector delivered on the promise of both improved part quality and lower cycle times. The stats here, sync was improved by 50%, part warpage was down 62%, and cycle time dropped a full 7 seconds, so 17%. The pictures here maybe deserve some explanation. The middle photo is the actual metal printed core. On the left is just a picture of the part, that's the refractor being molded, and the one on the right is a copy of the core, but it's done in clear plastic resin so that you can see the cooling channels inside a little better. A place where new machining efficiencies have been found is with the use of very special shaped cutters. Barrel tools, lens tools, oval tools, and now even tools with 3 different radius segments are available for purchase and can be utilized by Cimatron toolpath strategies. Using any of these cutters in the right situation is going to shorten your machining times while still keeping the same surface quality. When compared to machining with a standard ball tool, a combination of lens and then oval cutter on this mold insert cuts finishing time by more than half. It's due, of course, to utilizing the larger curvature radius of the cutter in its optimal geometric zone. A lot of the machining that mold parts require is a good fit for these special cutters. And while they're currently more expensive than regular ball cutters, it's a great way to cut time on the CNC machine. Having the ability to utilize these new cutter shapes is an important feature for your NC software. And there is more to show, a lot more, but at this time, I'll wrap up the presentation for today. Those 5 key elements we identified earlier as essential for staying competitive in the 21st century mold making industry, you'll find them in Cimatron. And we'd be happy to talk with you about your process and show you how we can help.